So what we want to look at today, again, is exponential graphs. Just like I expected you in the last unit to recognize a polynomial graph at a glance. Polynomial graphs, we had several options. Don't write this down. But for polynomial functions, we said, hey, that's too light for you guys to see, isn't it? Let's go darker. We said, hey, that can be a polynomial function. That's a linear polynomial function. That can be a polynomial function. That was the constant polynomial function. That was like y equals 5 or something like that. Smiling? Is somebody else trying to come in late? Okay. Oh, that can be a polynomial function. What was the degree? 2. That's a quadratic. And then we got as far as looking at cubics, which kind of looked like that. Okay. What was not a polynomial function? Well, we said something like that. We had all sorts of weird ones. I'm also going to expect you to recognize an exponential function. So example A says, circle the exponential functions. Is graph A an exponential function? Justin, does graph A match what every single exponential graph looks like? Yes. Good to see Jake leaned his head back already. He's learning. Could you show me what that graph looks like? Okay, so let's circle that one. Is graph B an exponential function? No. What is graph B? Get your calculators out, please. Does anybody know what that graph there is? Jacob, say what? Speak to me. Nice! I am impressed. If you go to the graph menu and you type in second function square root, which is second function x squared, of x. Oh, and then don't forget to go view windows standard, just in case your view windows have changed. I know mine does all the time. Yeah, square root graph. So you can put an x through b, but if you want to, you can say, hey, this is y equals root x. This used to be part of the curriculum. It's not anymore. I used to actually teach my students. We called it the wounded seagull graph because it was a seagull coming towards you, and then you lopped a wing off. There was the square root. It was the wounded seagull. It's graphic, but it worked, right? What about graph C? Is that an exponential graph? No. Let's cross out the letter C. I know what equation that is, though. That's a constant function. How high is that graph? Can you zoom in and read? I tried. Sorry? This is actually y equals -2. This is a polynomial function. We called it the constant function. Okay, but it's not an exponential graph. What about graph D? Pardon me? Yes? What about graph E? Yep. What about graph F? Nope, this is some type of a parabola. It has a vertex of 2, 8. Yep, it's got a negative in front of the x squared. It opens downwards, all that stuff. Okay. Oh, there's more, Mr. Dueck. You were really busy when you were typing. Exponential? Nope, this is a linear. In fact, you know what? Next to F, let's even write quadratic or parabola. What about H? Exponential? Nope. What kind? This is probably a cubic. In fact, I would even say this is a, since it goes that way, it's a negative x cubed. The same way as right above it, I would know that that's a negative x squared because the parabola opens down. What about I? Yes, exponential. Whoop. What about J? Does that look exactly like every exponential graph? Now, here's what we said. Every exponential graph gets closer and closer to 0 going this way. And we said that they go through either 0, actually, no, we said the y-intercept was 0, a, where a was the number in front of the base. You going to make it, Foster? You look a little tired there. You good? Mm-hmm. because I'll bring it on if I have to, but you can try. You're good? All right. Does that match our exponential? This is not an exponential. This is actually, believe it or not, a log function, which we'll be looking at later on this unit. It's an inverse of an exponential, and it's probably the single most complicated function we'll look at all year. Yeah, turn the page. So example 1 says this. Predict, which means we're going to try and do this without our graphing calculators first. The number of x-intercepts, the y-intercept, the end behavior, the domain, the range, and whether this function is increasing or decreasing. In fact, the very first thing we're going to do over here is a little sketch. Don't write a little graph there, but then don't write this next bit down. We said every single exponential function looks like that or looks like that. They're either increasing or they're decreasing. Psst. They're increasing or they're decreasing. So here's my question. This one here, is it increasing or decreasing? Is it going to start small and get bigger, or is it going to start big and get smaller? And how can you tell? You can. What's the base of this exponent? Bigger than 1 or smaller than 1? That 2/3. Fractional base, that means it's, if it's bigger than 1, that means it's increasing. As a graph, now you guys can draw this, it's going to look like that. That already tells us the first bit. It says predict the number of x-intercepts. So how many x-intercepts will this graph have? It's a trick question. None. There is a y-intercept right there. Who remembers the trick for finding the y-intercept? 0,9. We said the y-intercept was that there. And you can realize, you can calculate it, because to find the y-intercept, you put a 0 in for x. What's 2/3 to the 0? What's anything to the 0 power? 1, not 0. What's anything to the 0 power? 1. What's 9 times 1? 9. When x is 0, y is 9. In fact, we can even label that on our graph right now. 0,9 sits right there. Next thing it wants is the end behavior. From what quadrant to what quadrant? Domain. How far left, how far right? Infinity, all reals. Range. How high? Forever, positive infinity. How low? Gets closer and closer and closer to 0, but never touches. So it's everything above, but not including 0. Range is y. Above is greater than. If it was touching 0, we'd add that, but it never touches 0, so don't add the line. 0. And then the last one, increasing or decreasing. Fancy word, decay. This is a decay graph. This is exponential decay. Now, we've made our predictions. Let's actually see if we're right. Let's get out our graphing calculator. Clear any graph that I have here. By the way, to go from graph to back to the screen, hit F6. That says go from graph to where you type in a table or an equation. That's what that G arrow T means. It's going to be 9 bracket 2 fraction button 3 close bracket to the power of x. There's our function. Draw. Again, don't let the graph fool you. It looks like it's touching 0 right there. That's because the screens are crappy. These are not retina screens or anything like that. These don't have a whole bunch of pixels. They're cheap for a reason, but it's good enough. I get the shape. Oh, there's my Y-intercept. Heck, if I go trace and I type in x equals 0, sure enough, y equals 9. Or I could use, under gsolve, I could use the Y-intercept feature, but sometimes it's easier to just go trace 0. I can look for x-intercepts, roots, and it'll say are none. So we're right. Example 2. Put your pencils down for a second, please. You may recall in the last lesson, I gave you an example where we looked at bacteria. I think it was Connor was our yes, he was our researcher, okay? And so I wrote this. He wanted to find the growth rate, so he isolated 3 cells, and he noticed the following pattern. After 1 hour, there was 6. After 2 hours, there was 12. After 3 hours, there was 24. After 4 hours, how many? 48. Now, in real life, here's what this is saying. After 1 hour, after 59 minutes, there was still 3 cells. After 59 minutes and 30 seconds, there was still 3 cells. After 59 minutes and 59 seconds, there was still 3 cells. After 1 hour, boom, now there's 6. Then after 1 hour, 1 minute, still 6. After 1 hour, 30 minutes, still 6. After 1 hour, 45 minutes, still 6. After 1 hour, 50 minutes, still 6. After 1 hour, 59 minutes, still 6. After 2 hours, boom, now there's 12. Mathematically, what this was saying is there was no growth between hours, and the growth only occurred right on the hour. Is that really how populations work? Nothing happens, nothing happens, nothing happens, nothing happens, and then suddenly the cells divide? Or are they continuously dividing all the time? Okay. In large populations, say like the human race, babies are being created, babies are being born all the time. Babies are being, in cell populations, cells are dividing all the time. Now, mathematically, it was easier to pretend that they were doubling every 2 hours or every 1 hour to get nice numbers, but really, that's not what's happening. It turns out, using a base of 2, like I did for this example, doesn't model a population very well because it's suggesting, Jake, that no growth occurs between the hours and all of the growth instantly occurs on the hour. That's not realistic. It turns out there is a base called the continuous growth base that best models populations that are increasing continuously. And it's such an important number that, like pi, it has its own symbol. And the symbol is E, lowercase. Or now pick up your pencils. This is the continuous growth base. Hugely important. Brooke, if I'm going into any kind of medical research or population research or almost anything where there's growth or decay, I'm going to find that the best number to model, the best base in my y equals a b to the x equation, the best number to put where b is not 2. Is not 3, not a half, it's not a quarter, it's E. I know it sounds strange to say E is a number, but E is a number. What number is it, you ask? What number is it, you ask? So glad you asked. If you get your calculators out, and you go to the menu, the math where you type in stuff, okay? If you look, here's your X button, here's a button called log. Right here is ln, and right above it is e to the x. If you go second function, that, and you go e to the power of 1, that actually tells you the value of e, because anything to the 1 is itself. Turns out the number that best describes population growth, I didn't say it was a convenient number, just like pi is not a convenient number for looking at circles. It's irrational, it goes on forever, but it's the best number, is e. E is 2.7182818, and you start to think that it repeats, but it does not. It doesn't go 1828, 1828. Right off the screen, right here, it goes all haywire like pi does. It goes on forever and ever and ever without repeating. I'm a nerd. I had to introduce it. Also, the textbook is going to introduce it. So this is where your E button is. It's right there. We can already predict what this graph looks like, though. You ready? The base, y equals e to the x, is what we're graphing. What number is e? Bigger than 1 or smaller than 1? Bigger. So will this be a growth or a decay graph? Growth. As a graph, it's going to look like that. It's not going to be getting smaller. It's going to be getting bigger. It's going to have a Y-intercept. It's going to have, well, let's see if we can answer everything. First of all, it says predict the number of X-intercepts. How many X-intercepts? None. What's the Y-intercept? Well, the Y-intercept is the number sitting in front of the base. What number is sitting right there? It's invisible. Yeah, this is going to have a Y-intercept of 0, 1. Oh. End behavior. Still quadrant 2 to quadrant 1. Domain. All reals. Range. This is getting repetitive, Mr. Dueck. Everything. Mr. Dueck, is the range of an exponential graph just always going to be above 0? Well, if we keep it simple, yeah. But remember how you learned how to slide a parabola around by moving it up and down and left and right? We could apply some of those same things to an exponential. I don't think we will be. Could. Then it says, verify your predictions by creating a table of values. You know what? I'm not going to do a table of values. Let's go to our graphing calculator. So let's go menu to our graph menu, delete this equation. You need to know how to find this magic E button. So if you didn't do it before, second function, ln, right next to the sign button, brings you little e, and it automatically does to the power of, so I'll just put the x there. And if I draw it, looks like that. When x equals 0, it goes through 1. There's my Y-intercept. When x equals 1, it goes through E, 2.718281828, and then it doesn't keep going 1828, 1828. It goes all haywire. Just unfortunately, just off the calculator screen is where it goes all haywire. This number, by the way, appears all over the place, the number E. So if I'm, for example, trying to model the spread of a disease in a country, the best equation to model that, it turns out, will have a base of E. If I'm trying to model how scores are distributed on the English 12 provincial exam, it turns out, believe it or not, the best model is E. You all were in Foundations of Math 11 last year. Remember this thing here, that bell-shaped curve, z-scores? Turns out that graph has E in its equation when you try and generate it on a graphing calculator. It shows up all over the place. Example 3 says, which exponential function matches each graph below? Okay. You ready? We're going to do this without graphing calculators. We're going to do this by a process of elimination. And the first thing we're going to look at are the bases. Now, the bases are that, and that. There are two types of bases for exponential functions. Smaller than 1, fractions or decimals, or bigger than 1. Which ones are smaller than 1? A, B, C, or D? Okay, Vaughn? Guys, I want you here, please. Which bases are smaller than 1? Okay, A and C. Those are going to look similar. those are going to be decay. In fact, I'm going to write next to here decay. Decay. They're going to be decreasing. They're going to be getting smaller. These ones are going to be growth. In other words, I can already tell you that B and D go with graph 2 and graph 4, and A and C go with graph 1 and graph 3 because they're decay. Now, how else can I figure out what graph goes with what? The Y-intercept, the Y-intercept, the Y-intercept, the Y-intercept. So graph number 1 is going to be a decay graph. It's going to be getting smaller, and it's got a Y-intercept of what? 0, 3. So let's find the decay graph that has a Y-intercept of 0, 3. Which one? Has to be that one. Decay and Y-intercept. Try the rest of these on your own. I'll slowly fill them in as well. See if you can get all 4. Thanks, kiddo. See you later. So I ended up with A being graph number 3, B being graph number 4, C being graph number 1, D being graph number 2. On your test, I'll definitely give you some graphs to pick from, and I'll say, mix and match, tell me which ones go with which. This method is way faster than trying to graph each one of these. Also, when you graph them on your graphing calculator, the resolution is pretty poor. It's kind of tough to tell. You can tell whether it's growth or decay, but finding other information can be tricky. So, try this next one as well on your own. Turn the page. I'm going to freeze the screen this time. Treat this like a mini quiz. See if you can get the same thing that I do. So it says match each function with the corresponding graph below. Provide your reasoning. You don't have to provide your reasoning. You can if you want to as little notes. So look at the base. Look at the Y-intercept, the coefficient. Wait a minute. Totally writing this down wrong. All right, let's try that again, Mr. Dueck. That graph there goes with that graph there. Read the question properly. That graph there goes with that graph there. That graph there goes with that graph there. And that graph there goes with that graph there. So when all's said and done, is that right? I think. Okay. Let's summarize. In summary, there are two main types of graphs. If we have, they all look like this. Y equals a bracket b to the x. There's our exponential template, our pattern. Where, remember, I did have to give you some restrictions. I did have to say a can't be 0. Sorry, let me try that again. A is bigger than 0. A is positive. Can't be 0. And we're not going to deal with negatives. By the way, a negative just flips everything, but it's confusing. So we're going to keep it positive for now. We're going to keep the base positive. We said we're not going to put in a negative inside the brackets. And then which number as a base doesn't behave properly? Which number, when you use the exponent rules, doesn't quite work? What? Yeah, we said, I'm being fussy, but just remember, what I'm showing you works in those situations. So please don't put a negative in front of everything. By the way, if you're really wondering what does a negative do, negative. Just like a parabola, it flips it. Not that big a surprise, actually, but we're not going to go there for a while. Okay. The y-intercept is 0, a. X-intercept is, by the way, I'm going to be a little bit fussy. Put none. If it says how many x-intercepts, write none, not 0, because if you write 0, you could be saying the x-intercept is 0, 0. We'll write the word none. End behavior goes from there to there. Domain, all reals. Range, everything above but not including 0. And then there's two main types of graphs. Growth or increasing, decay or decreasing. What's the difference? The base. The base. If the base is bigger than 1, it's going to look like that. Example, y equals 5 to the x. Now, if the base is less than 1, wait a minute, I also have to somehow say that the base is positive. You know what? Look up. If the base is between 0 and 1, there, if the base is a positive fraction. Okay, if the base is between 0 and 1, it's going to look like this. Example, y equals 4 bracket 1/3 to the x. That would have a y-intercept of 0, 4, and that would be a decay function. Whereas the previous one would have an x-intercept of y-intercept of 0, 1, because there's nothing in front of the 5, an invisible 1 in front of the 5. growth, decay. Most of this is a repeat of what we've talked about. Occasionally you'll be asked to sketch a graph, but most of the time it's going to give you a graph and it's going to say, hey, can you tell me the domain, the range? It's going to be very repetitive. I'm doing that on purpose. I want this to almost become boring. Now, next lesson, we're going to start to look at, okay, what if they give me a bunch of data, just like we did in the last unit, and I graph that data, so we put that into our stat feature, and instead of it looking like a parabola, instead of it looking linear, what if it looks exponential? How can I find the best fit equation? Tune in next week, tune in Wednesday, and find out. Our goal, by the way, is no homework for the long weekend, so make sure you come on time Wednesday, prepared to get lots of work done, because we want, you guys have a 4-day weekend. It's Easter weekend. That's what we want to keep free.